Hello. Today we'll be going over the 2019 AP Physics 1 practice exam. And just a disclaimer, I'll be skipping all problems. Since this test is a little outdated, I'll be skipping all problems related to electricity, circuits, or waves, since those 3 units were removed as of 2020. So let's just get right into it. So number 1 is a collision. And which of the following object motion after the collision? Okay, so we know 4 kilogram. So we know a 4 kilogram is moving to the left and 3 kilogram is moving to the right. So all we're given is their masses, so we don't even know the initial momentum, so that wouldn't allow us to know the final momentum or the final velocities of the systems. So yeah, it cannot be determined. D is the answer. Okay, so brother and sister are standing next to each other at rest on a frictionless ice. The brother's mass is exactly twice. Sister pushes her brother. Okay, so let's see, the 2m is the brother and m is the sister. So the sister pushes her brother and then she moves with kinetic energy k. So first of all, momentum is conserved. So if she is moving over with mv, he's moving 1/2 v over here. So 1/2 mv squared is equal to k. So what's this? 1/2 2m 1/4 v squared is equal to 1/2 times 1/2 mv squared. So that's equal to 1/2 k. So C is the answer. Okay, so at time t, a car is at x equals 10 and has velocity of 3 in the negative x direction. Car has a constant acceleration with magnitude 3 to 6, which the following gives the possible ranges at t equals 1. So we could use delta x equals v0t plus 1/2 at squared. So v naught is -3 and t is 1. And then for a, let's just try out the minimum and maximum accelerations. So let's do 3. So one possible value of delta x when acceleration is 3 is -3 plus 1.5, that's -3/2. And then -3/2 of 10 is 8.5. Sorry, 10 minus 3/2. And then another possible value is 1/2 times 6. That's delta x equals 0. So it's just 10. So B. So we're going to skip 4 because it's a circuit problem. And then let's move on to 5. Okay, so this is a graph of potential energy. Point H, the object is moving, and mechanical energy is 5. Okay. This is the net force exerted have the greatest magnitude. So we're going to look at when so change in kinetic energy is directly proportional to the net force exerted on an object. So we're going to look at when which of these line segments has the biggest, let's see, change, like slope, I guess. So HI, it's not HI because that's flat. IJ has a slope of, the magnitude of its slope is 1. JL, it's flat. And LM, the magnitude of its slope is 3. or sorry, this is 2 and this is 3. So Lm has the greatest net force. So what is the kinetic energy of the object at point K? So at point K, let's see, the total energy is 5 joules at all times. And at point K, the potential energy is 2 joules. So that means that the kinetic energy is 3 joules. So for number 7, which of the following describes the magnitude and momentum of the object in the first 2 straight line segments shown in the graph as the object moves from point H to point J? So at HI, there is no change in kinetic energy, but there is kinetic energy. So the momentum is constant but non-zero. And then IJ, you're decreasing your potential energy, so that means you're increasing your kinetic energy. So that means it's increasing. So C is the answer. Number 8. 8 is a wave problem, so we'll skip that. So is 10 and 11. 10 is a wave problem, and 11 is a resistor problem. So 12. A toy doll and a robot are standing on a frictionless surface. Okay. So 0.2 and 0.3. Robot pushes with 0.3 newtons. So that means 0.3 newtons are exerted back. And then F equals ma. So 0.3 newtons equals 0.3 kilograms times A. A is 1. A block of mass m travels with speed v0 to the right, and it collides elastically. Which of the following describes the speed and direction of the block and the speed of the sphere a short time after the collision? Okay. So initial momentum is mv0, and then okay. So since it's an elastic collision, momentum and kinetic energy must be conserved. So let's just test that. So initial momentum is mv0. So final momentum should be just that. So let's see, if it's negative mv0 over 3 plus 4v0 over 3, that's true. Let's see if it's mv0 over 3 plus 4v0 over 3, that's not true. Let's see if it's 0, and then 2mv0, that's not true. And then if it's negative mv0 plus 0, that's not true. So A is the only answer choice in which momentum is conserved. A block of mass m slides along a frictionless surface with kinetic energy K initial, collides with a block of mass 3m, and they stick together and slide with the total kinetic energy. So let's just say it's moving with velocity v, and then it collides and then they stick together, so it's like that. So Vf is equal to Vi over 4. So if Ki is 1/2 Vi squared and Kf is 1/2 4m Vi over 4 squared, that's equal to 1/4 Ki. So 1/4 Ki to Ki is equal to 1 to 4. D. So a meteoroid is in a circular orbit 600 kilometers above the surface of a distant planet. The planet has the same mass as Earth, but has a radius approximately 90% of Earth's. Acceleration of the meteoroid due to gravitational force is... Okay. So... meteoroid is... So it has the same mass, but the radius is a little smaller. So let's see what's 90% of... Let's see what's 90% of 6,400. Where 10% of that is 640. So if you just subtract 6,400 minus 640, you get 6, 7, 5, 7, 60. Okay. 637. So it's 637 kilometers. Sorry, ignore what I just did. So this planet is 637 kilometers smaller than Earth, but it's above 600. So it's still smaller than Earth. So since the radius is smaller and gravitational acceleration is equal to gm over r squared, since the radius gets smaller, this should increase. So it's C, because gravitational acceleration is always directed towards the center of the orbit. Does the planet exert a torque on the meteoroid with respect to the center of mass? No, it does not. And D is the correct answer, because the planet exerts a force towards the center of the mass of the planet, but it's parallel to the meteoroid's position vector. So there's no perpendicular component to the force, so the torque is 0. A satellite in orbit around Earth is initially not rotating with respect to its center of mass. Two identical thrusters on opposite sides of the satellite fire in opposite directions over the same 10-minute time interval. How does the firing of the thrusters affect the mechanical energy of the satellite Earth system and the shape of its orbit? Okay, so these thrusters, they just cause the satellite, they just provide a torque and they cause the satellite to rotate. So the satellite will gain rotational kinetic energy, so that will increase the satellite Earth system. And would it affect the change of the orbit? Well, the thrusters are in opposite directions. So there's no net force on the satellite. So the orbital path will not change. 18, we can skip. 19. After release, at what height will the kinetic energy of the block be maximum? So it's compressed to 1/2 L EQ minus L comp squared equals 1/2 V squared. And V equals square root of 2GH. So 2GH So mgh is equal to k squared, which is equal to 1/2 kx squared over 2 mg. Oh, okay. Sorry, I did this all wrong. So kinetic energy will be max at LEQ because this is the equilibrium position, since that's when we put the block in. So that's when kinetic energy will be its maximum, because all the spring potential energy will be converted into kinetic energy. But once you get above this, kinetic energy starts being converted into gravitational energy, so it decreases. So that's why at its maximum, it's at the equilibrium position. Okay, 2 frictionless lab carts start from rest. Which car has the greatest kinetic energy at the end of the push? So they still have the same impulse, 10, but they have different masses. So the speed of this one is 10, and the speed of this one is 5. So 1/2 to 5 squared is 25. So cart 1 is the greater kinetic energy. Okay. A simple pendulum consists of a sphere at which angle with the horizontal will the kinetic energy and the potential energy be equal. So let's say it's pulled back until the spring is horizontal. And let's say this is the natural length. So when it's pulled back, when half of the when the kinetic energy and potential energy are equal, that means it's halfway above its peak and its starting point. So it's like right here. So what's this angle? So let's see. This is L. This is L over 2. This is L. So that means this is L squared. What's this? L squared over 4. That's 3L squared over 4. This is square root of 3 over 2L. So this angle is greater than 45. So that means that this angle is less than 45. So C is the answer. 22. A stationary cart attached to a force gauge is on a straight horizontal frictionless track. A student uses the force gauge to move the cart and produces the force as a function of time. So force time graphs can give you impulse if you find the area under the curve. So let's just find the area under the curve from 0 to 20. It's about 15 times 4, that's like 60. And then like 5 times 8, that's like 40. So it increases. So yeah, okay, so it increases and then decreases without changing direction, because it only decreases by 40, but the net impulse never becomes negative. Okay. This is a velocity time graph. Which of the following time intervals does it return to its position? So the area under a velocity time graph is displacement. So when the net area under the curve is 0, that means it returns to that means the displacement is 0, and it returns to its position at t equals 0. So first it goes like there. So I think I'll finish about here. So I'd say it's about 4 dots up. So I'd say this is about between 7 and 10. Okay. And then number 24 is a wave problem, and 25, so we'll skip those. Okay, so for number 26, this is an amusement park ride in which a passenger is riding at constant speed in a circle. So this is uniform circular motion, so even though the speed is constant, the velocity is changing because the direction is always changing. And since it's constant speed, the angular velocity is constant. So what is the normal force passing at point D? So at point A, the C exerts a force of 0.8 of F of G and F of G. So the centripetal force is 0.2 F of G. So at point D, there's F of G. So that means the normal force has to be 1.2 F of G in order for the centripetal force to be constant. So D is the answer. And 28, the kinetic energy of the rock when it's at the same height as point D is most nearly. So the person releases the rock while passing through point A. So when it's passing through point A, it has kinetic energy and potential energy. So its kinetic energy is just 1/2 mv squared, and then its potential energy is 2r plus mg 2r. So if you factor out a 1/2 m, you get v squared plus 4gr. That's D. These two are electricity and circuit problems. Okay, 31. Okay, so which of the following ranks the elastic potential energy in the 3 positions? So elastic potential energy is 1/2 kx squared. So basically, which of these displaces the most? So it's not Z. Okay, well, so we don't know that what x is when the object is hanging from the spring in equilibrium. But we do know that for point Z, the spring will be stretched so that x will be increased by an amount that's less than D. And for point Y, the spring is stretched so that x is increased by an amount greater than D. So Y is the most, and then X, and then Z. So C is the answer. So a projectile is launched from the top of a cliff. Horizontal displacement and vertical velocity. So horizontal displacement is constant because, or it's increasing at a constant rate because horizontal velocity is constant. And the vertical velocity, it is it's initially negative and it gets more and more negative, so A is the answer. The graph above represents the position of 2 identical carts, which are flying about the magnitude of the position's center of mass. Okay, so at point T, during this, the slope is 1/2, and the slope of this is 1/2, and during this, the slope is 0, and the slope for this is 2/3. Okay. So let's see. So the center of mass decreases because the total velocity for initially is 1 and then it becomes 2/3. Okay, so for number 34, it's asking for what's the change in kinetic energy. So the initial kinetic energy is just from this first sphere, because it's the only one moving. So it's 1/2 mv squared. And then the final velocity is mv1 equals 3 mvf. So vf is equal to initial velocity over 3. So its final mass is 3m, and the final velocity is v initial over 3. So it's 1/3 of k initial is k final. So negative 2/3 is the change in kinetic energy. Okay. So 35. A sphere with a radius 0.33 meters and rotational inertia spins on an axle with an initial angular speed. Okay. So we can find the angular acceleration by just finding the change in angular speed. So the initial angular speed is 3, and then final is 0, and that's in 6 seconds. So angular acceleration is negative 0.5. And then we know that torque is equal to rotational inertia times angular acceleration. So that is 2 times negative 0.5. And that is negative 1. But our angular acceleration was kind of well, the torque is negative 1, but the torque to slow it down it kind of implicates that it's negative. So it's B. 3 blocks are pushed. What is the for free body diagram for block B? Okay. So for block 1, there's P, and there's friction, and there's block 2. For block 2, there's block 1, friction, and block 3. And then for block 3, there's friction and block 2. Okay, well, block 2, they call it FSE, and then it has the gravity and normal force, but C is the answer. Yeah, block slides down an inclined plane. Which of the following information is needed to determine whether the velocity is constant? Okay. So we can use Newton's second law to determine if the acceleration of the block is 0. Since we know that for an inclined plane, it's mg sine theta going down, and then if there's friction, it's friction mg cosine theta, and then we can get that acceleration is equal to g sine theta minus mu cosine theta. So if we know the angle, that will help us. And then also the coefficient of friction, because we don't know mu. Okay. So a test car and its driver with combined mass 600 are traveling. Okay. So the length of the skid marks are needed because because force times displacement shows like the work done, and the work energy theorem states that the work done on a system is equal to the change in energy. So, and then also the force that is providing the stoppage is the force of friction, and it's kinetic friction because the car is moving, so we'd like to know the coefficient of kinetic friction. 133 is a wave problem, so we can skip that. Okay, so for this final problem, we can see that f of 1 is equal to f of 4. Sorry, f of 1 is equal to f of 4, and f of 1 is equal to 2 f of 2. So that means that 2 f of 2 is equal to f of 4. So f of 4 sine 30 is equal to 2 f of 2 sine 30, which is equal to f of 2. So f of 2 and f of 4 can produce a net torque of 0 because f of 2, they're the same distance from the center, which is r over 2, and they have the same force, perpendicular force. So that's it for this 2019 AP Physics 1 practice exam. Leave any questions in the comments, and hope you enjoyed. Thank you.